Hello, honors physics students. Please make sure you have your notes in front of you, specifically the notes page on sign conventions and image descriptions, as well as the notes page you just completed on drawing your ray diagrams, and you want your optics practice problems in front of you. Okay, so the other day after test, I went through the first lesson here, and I gave you some of the equations. Specifically, magnification is negative di over do, also equal to hi over ho, and 1 over do plus 1 over di equals 1 over f. And I asked you to just complete the math for problem number 1 just to get a sense of how that all works. And we already did that, so here on problem 1 you should already... Here we go. That you measured the object height, that's the height of the arrow here, is 1.9 centimeters. We all agreed on that. You calculated di is positive 8.57 centimeters. You calculated magnification is negative 0.714. And from this, we applied this to get the height of the image as negative 1.4 centimeters. Here I'm putting the positive sign on di because now we see from our sign conventions list that's important for us to know the signs on these numbers so we can correlate them to our sign conventions and image descriptions. We only use 2 sig figs here because we only measured HO to 2 sig figs. I'm not sure you could really get more than 2 sig figs. You probably can, maybe you can, but I think for our purposes, let's just do it all the same so we can correlate them. Okay, so now the first thing we want to do before we do the ray diagram is make a prediction as to what this image should look like. So we have our 3 categories of image descriptions, and so let's go through them. The first one is upright or inverted, and so we're looking at the signs and the numbers involved in our calculations here. So there's a bunch of ways to do this. We could say magnification is negative. Anytime you have a negative magnification, that means that one of the heights has been flipped relative to the others. We are expecting it to be inverted. Also, we got a positive image distance that goes along with inverted as well. For magnify, reduce, or life size, well, look at the absolute value magnification, even though, disregard the negative sign, just the fact that it's a number less than 1 indicates that it's supposed to be a reduced image, because it's just a ratio of 0.714, and of course we saw this with HI as well. HI is literally smaller than HO, so it's expected to be reduced. Don't worry about the negative sign, just tells you the orientation. And then the real, well, for a single device, real goes with inverted. Once again, with our positive image distance, that means that we're expecting the light to actually go to where a screen would be placed. So that's on the side of the mirror where the light actually ends up. And so we call that the real side, and real and inverted always go together. So here's our prediction as to what the image should look like. Now we're going to do our ray diagram. So I want you to pause the video, try to go through the rays as we learned in the last video as best you can, and see where they meet, and draw your image, and come back and I'll lead you through to make sure we're on the right track. Well, we don't have to go in the order I presented in the last video, but I'm just going to go in the same order just so we can review that. So the first one is the parallel. So we start always from the tip of the object. We always want to locate the image of the tip of the object. So we start here parallel to the principal axis. Here's a little pro tip though, just to help you out. If you're using your straight edge, when you place your straight edge here and your straight edge obscures the principal axis, you're going to have a tough time making this line parallel to the principal axis. So a pro tip is to hold your straight edge here so the bottom edge of it is what you're going to use to draw your parallel ray, so you can see whether it's parallel to the principal axis. Alternatively, of course, if you happen to have a clear straight edge, well then, you're doing just fine. Okay, so here's our parallel ray. We know the parallel ray is going to go through the focal point. The focal point is clearly marked here on the principal axis, and so you have to make sure you go right through it, right? You can't go to the left of it, the right of it. You're not going to go to R, that's twice F. You can go right through it, and also make sure you're putting arrows on your rays. If I do arrows, you do arrows. I'm teaching you a new skill, so you have to do the ray diagrams exactly the way I do. This being one of our first ray diagrams, you don't know how much of the reflected ray to draw, so just draw a really long reflected ray. Our second one is the central ray. For this one, you have to hit the exact center of the mirror. That's where, in this case, the left edge of the mirror intersects the principal axis. If you measure, you'll see that the tick marks are evenly spaced, and this tick mark is measured from the left side, or the front side of the mirror, if you want to think of it that way, the way the light is approaching. So you have to hit directly there. With my drawing tools, I couldn't quite hit there, so you need to get a little bit better about that, going from the tip of the arrow right to the center of the mirror. So here's where you employ the trick of constructing the equal angles. This is where you measure the size of the object, which we already know is 1.9 centimeters, and then you measure down from the principal axis that same distance, the 1.9 centimeters. You're going to put a single dot there. Do not draw the object underneath the principal axis. If you did that, you've got to erase it immediately. Because if you draw the object underneath, you might think that's the image. And I've seen students do that, so don't do that. Just measure 1.9 centimeters down, put a single dot there, and then just connect the dots from the center of the mirror over to that. So here's my dot, and then I intersect it like so. And you can see that I'm constructing the equal angles by doing so. No need to measure with the protractor. There's a nice little trick that gets it there. Now at this point, we could actually be done. Anytime you have 2 rays that start from the same point in the object and intersect, you could be done right now. And so you can just draw your image right there. But, for practice, it's a good idea to draw the focal ray. As you do more and more ray diagrams, you'll find you're just more successful doing certain rays rather than others. And so go ahead and draw, if you haven't already, the focal ray, which means we start from the tip of the object and we have to go through F, right? That's what the focal ray means, going right through F. And then it comes out, or reflects parallel to the principal axis. And you notice when I do it, all three might intersect. Now, this being your first ray diagram on your own, if all three of them don't quite intersect, don't fear. You'll get better as you go. In the end, remember, you only need 2 of them to intersect anyway, so the third one could act as a check. And you may find you're just better at some than others. Okay, so they should intersect over here. And as we did in the past video, we're going to draw the image from the principal axis to the intersection point, like so. And then it's a good idea to label it as image. Label this as object, this is image. Alright, so now let's see if our predictions came true. We predicted inverted. Well, look, our object is pointing up, our image is pointing down. That's looking good. We predicted reduced. Clearly this is smaller than that one. And we predicted real. That means that these light rays actually intersect here. If I were to put a screen here, I get an image onto that screen. Yes, that works perfectly. I know we haven't seen a virtual image yet, but we'll see one soon. You'll see what that means to be virtual. We can even look at the numbers, right? If the radius here is 10 centimeters, and it means the focal length is 5, so here's 5, here's 10. Does this look like it's about 8.57? Maybe not quite exactly, but you know what? It seems to be pretty close. That's the general idea. And so this is why I always want you to do the math for a problem first. You're going to get the math right. Right? And then if you're not quite good at doing ray diagrams, well, you know what? By doing the math here, you can actually know where the image is supposed to be, and then you can sort of make the ray diagram happen around it. I wouldn't prefer you do it that way, but you know what? Do the math first. All right, so we're going to go on to problem 2. Now, problem 2 is a little bit different. This one's drawn exactly to scale. So first you're going to be measuring things. Measure DO, measure HO, measure F. Measure all those things first. We'll agree on them together, and then we'll do the calculations. Okay, so I measured DO, HO of course is 1.9 because I just copied and pasted, right? So every object in this works. I measured DO to be 1.0. Now we're measuring from the left side of the mirror like I mentioned before. So make sure you're measuring from here to there. And we all should agree on 1.0 centimeters. For the focal length, it should be 2.5 centimeters. I'm putting a positive here to indicate it is a positive mirror, right? It's a converging mirror, a concave mirror. And measure again. If you didn't get 2.5, I'll go ahead and do your calculations to calculate DI, magnification, and HI. Make sure you put proper signs on everything. So we should be getting these. We should be getting DI is negative 1.7, magnification is positive 1.7, HI is positive 3.2 centimeters. Please make sure you're putting your signs. These are not vector quantities, but the signs will help us make our predictions. Okay. Now at this point, pause the video, make your predictions as to the image description. We're doing one from each category. So we should be predicting uprights. We are getting a positive magnification. It should be getting magnified because we're getting a number larger than 1, and virtual because we're getting a positive magnification or a negative image distance. So we're actually expecting the image to appear on the wrong side of the mirror. Alright, so pause the video, start to do your ray diagram. I suggest doing your first 2. I'll talk about why doing the focal ray is going to be a little bit tough. Okay, so here's my parallel ray going through the focal point. Here's my central ray. I've measured this, I put the dot there, and I made this happen here. Drawing the focal ray is rather difficult because if you start from the tip of the object and go this way through the focal point, what's the problem there? Well, notice we're actually moving away from the mirror, and the whole point is to reflect off the mirror. So obviously that's not how it's done. So don't do that. Because remember, it doesn't matter. All we need are 2 rays to reflect off the mirror and intersect, and wherever they intersect, that's where the image forms. But of course you see they're not intersecting, right? That's a problem. In fact, these rays are spreading apart. They are diverging from each other. So what do we do? Well, here we go with our idea that, remember, when it comes to light, humans are stupid. That's right. Remember, we're stupid. We're very easily fooled. So imagine we're standing over here. That's where our head is. And here's this object. Here's the mirror we're looking at. And we're trying to get an image of the mirror from this object. These light rays are coming at us. And remember, we think light rays come to us in straight lines. So what do? We take these reflected rays and we trace them backwards into mirror world. Make sure we are tracing the reflected rays backwards, not the original rays, right? And just like I did before, I'm using dashed lines because these are imaginary. Light rays don't actually come from there. And there's no arrows on these ones, where there's arrows on every single one of these rays, and you should draw those. And there's no arrows here because light doesn't actually do this. Light doesn't go through mirrors. And they certainly do intersect over here, so that's where the image forms. So you draw your image there behind the mirror. Okay, so let's look at our predictions. We predicted upright. Yep, it's pointing the same way. Magnified. Yep, it certainly is. Virtual. Yeah, Virtual means that if you were to put a screen back here behind the mirror, you can't get the image on the screen, which makes sense because light doesn't go through mirrors. Light doesn't actually travel this path. We just think it comes from there. Now, this doesn't mean you can't see the image. It just means that you can't get it onto a screen, or that we had to trace the light rays backwards to form it, or that we got a negative image distance. In fact, since these tick marks are evenly spaced, if this is 2.5, this is 2.5 behind, this looks like it's about 1.7, you know what? Measure it. Actually measure from the left side of the mirror back here. When I did it, I measured 2.0 centimeters. Oh, that's pretty close to 1.7. Measure the image height. We're predicting 3.2 centimeters. When I did mine, I got 3.7 centimeters, and you know what? That's not too bad. So it looks like all of our predictions came true. This is why you do the math first. Once you do the math, you already know, based on these numbers, exactly where it's supposed to appear. You can actually draw the image. Now, there is a way to do the focal ray. It's a little bit tougher, and honestly, for this one, it doesn't work very well, but I'm going to go through it. For the focal ray, we pretend a light ray comes from the focal point this way up through the tip of the arrow going towards the mirror. In fact, don't draw this one. I'm going to tell you right now, it doesn't work very well. If you do it, it goes like this, and then it's going to reflect backwards this way, parallel to the principal axis, and notice it diverges just like the others. If you were to trace it backwards, it should meet over here, but that really doesn't correlate with any of the others. And so for this one, the focal ray just doesn't work very well. So you know what? I wouldn't draw it all, because you don't need it. Okay, so I would just get rid of that, and actually I should have got rid of that one as well. Alright, let's go on to problem 3. Problem 3 is another one where we're just measuring the image height, and it's going to be 1.9 centimeters. Please feel free to verify. And then we're going to go ahead and do the math. Alright, so go ahead and pause the video, do the math for DI, magnification, and HI. Okay, so here's our calculations. We should be a negative 12.7, positive 0.363, positive 0.69, where again we're doing 2 sig figs here because we measured 2 sig figs in HO, but 3 sig figs in these ones because we're given 3 sig figs in the problem. Now pause the video and make your predictions. You should be getting upright, reduced, and virtual. Upright because magnification is positive, virtual goes with upright, negative image distance makes it virtual and upright as well. We have a magnification smaller than 1, or obviously a height that's smaller than the object height, so it's reduced. Alright, let's start to do our ray diagram. Let's start with the parallel ray. Okay, so pause the video and draw what you think happens. So if you drew it going this way, that's a problem. Yes, of course the focal point's over there because the focal point's always on the concave side of the mirror, but we've flipped the mirror around. It is now a convex, diverging mirror. The focal point's always going to be over here. This is not the focal point. Notice it's not labeled as focal point because that's wrong. But you can't have light doing this because, well, light doesn't go through mirrors. So what does it do? Well, if you go back to the first notes page from the other day, we know that all parallel rays of light, when they hit a convex mirror, diverge as if they came from the focal point. So it's going to go up and to the left as if it came from F on the wrong side. It's a negative focal length, right? Because R is negative 40, so F is negative 20. And so it's like it's on the wrong side of the mirror. So here's what we do. We draw a dashed line here, because the light doesn't really do this, and it reflects this way. Okay, go ahead and do the central ray. Now, nothing's different about the central ray. We're going to use the exact same tricks. So it's going to do this. You measure down here. We make the connection. We get our equal angles. No problem here. The focal ray is going to be a little bit tricky, but it doesn't matter. All we need are these two rays to converge, but notice they don't. They diverge. So what do we do? Well, what did we do before? We trace the rays backwards. So we trace this backwards. This reflected ray was already traced backwards, and here's the intersection point. That's where the image forms. There it is. Okay, let's do the focal ray. For this one, it's a bit weird. We start from the tip of the arrow, and we actually set up our straight edge so as if we're going to hit F on the other side. So we're aiming for F on the wrong side of the mirror. We stop it at the mirror because the light doesn't actually go through. We reflect back here parallel, and then when you trace it backwards, it should intersect the other two. So it's a little bit more of a challenging one. If you don't want to do it, that's okay. Let's look at our predictions. We predicted upright, you bet. We predicted reduced, yep. We predicted virtual, you bet. If I were to put a screen back here behind the mirror, light doesn't actually go through the mirror. There's no way to get the image onto the screen. That's definitely a virtual image. Doesn't mean you can't see it, just means it's virtual. If you look at the numbers here, if this is representing 20 centimeters, 12.7, okay, it's a little bit more than half. Yeah, it does. Everything's looking good. All right. You can even measure the height. When I measured my height, I got 0.7 centimeters. That's pretty close to 0.69. Okay, now, if I were to move the object forward or backwards along this axis, no matter what, these rays will certainly diverge. Whenever they diverge, that means that we're always going to trace them backwards, and so it's always going to be virtual. Virtual always goes with upright, and just based on the geometry, it's always going to be reduced. So it turns out diverging mirrors only produce one type of image, upright, reduced, and virtual. That's just what they do. No matter where we put the object, they'll always produce this sort of image. They can't do anything else.